What's the biggest question that you could possibly ask? Surely what it might be is, how did everything begin? That's a question that all origin stories ask, and they have a huge diversity of answers. Some say there wasn't a beginning because everything has always existed. Some say perhaps a multicolored serpent was traveling through the land, and as it did so, it created the mountains and the rivers and the streams and maybe even the stars and maybe even you and me. Some say there was a sort of committee of gods that created the world, or perhaps the one true God created the world. There's a huge diversity of these stories, but each of them makes claims. And that's because every origin story is, in a sense, an explanation. It's trying to tell you how things happened. And as a result of that, origin stories aren't fixed. They change. They change over time because new information comes in, new evidence, and the explanations have to change. Now, what we're going to look at in this unit is how the modern scientific answer to that great question emerged. And we'll see that new evidence over several hundred years changed the story. We'll begin by going back 500 years to Europe. And this is because modern science first flourished in Europe. Europe, at the time, 500 years ago, was predominantly a Christian region. And the Christian church, like most religions, had its own answers to that question, how did everything begin? And the Christian church's answer was that God created the universe several thousand years ago. But they tied that answer to a great model of the universe that had been constructed about 1900 years ago by an astronomer called Ptolemy, who lived in Alexandria in Egypt. Now, this is what Ptolemy's model of the universe looked like. He believed that the Earth was at the center of the universe, and the Earth was a realm of imperfection, and around it was the realm of perfection. And that realm consisted of several concentric, transparent spheres, and those spheres carried the sun, the moon, the stars, all the heavenly bodies, moving in different ways, depending on which sphere they were in. And then beyond them was the perfect realm of heaven. Now, Ptolemy's model of the universe worked pretty well. People accepted it not just because the church said they should, but also because there was a lot of evidence for it. And this was because astronomers in his time, or astronomers in the 16th century, I should say, and in Ptolemy's time, were studying the Earth using the naked eye. Now, think about this. If you were studying the universe using just the naked eye, just looking directly at the skies, you might be very tempted to think that the universe revolves around the Earth, mightn't you? Between 1550 and 1700, new evidence began to kick in, some of it supplied by new technologies, and what that did was it began to undermine Ptolemy's idea of the universe. Some astronomers, for example, pointed out that every year the planets, as they orbit the Earth, seem to move backwards for a period. And Ptolemy's model really struggled to explain that. The astronomer Copernicus in the 16th century pointed out that if you imagine that it's actually the sun that's at the center of the universe instead of the Earth, you can solve that problem quite easily. So that's one little glitch. Then another astronomer, Kepler, found that the orbits of the planets are actually not perfect circles, as Ptolemy had imagined. They are ellipses, ovals like this. Again, that was a problem. Third, an Italian astronomer called Galileo began to use what was the hot new technology of the time, the telescope. And he was one of the first astronomers to actually look at the heavens through the telescope. And what he saw showed the heavens were much less perfect than Ptolemy had thought. For example, if you look at the sun, it's got sunspots. These are real sort of blotches on the faces of the sun. No one liked that. And if you look at Jupiter, you find it's not a single planet. It's got little moons, lots of moons orbiting it. So for all of these reasons, people began to worry about Ptolemy's model and notice how new technologies, new evidence, and logic have begun to undermine a traditional explanation of how the universe works. Late in the 17th century, the great English scientist Isaac Newton began to argue that it wasn't concentric spheres that held together all the bodies of the universe. It was actually a mysterious force that pervaded the entire universe that was called gravity, and it pulled everything together. By 1700, most astronomers had dropped Ptolemy's model of the universe. They now came to believe there were no edges to the universe, there were no spheres, perhaps the entire universe was infinite in size and infinitely old and just held together by this force of gravity. Now, notice how evidence has begun to change the old story. This is in fact the first model of the universe that was scientific in the sense that it was based primarily on evidence. And notice one more thing. Notice how scientists in different parts of the world communicate with each other, share their information, share their evidence to construct a new story. This is the process that we're going to call in this course collective learning. And here's a very powerful example of how it works. Let's call this model of the universe we've just been describing Newton's universe. It described the universe as infinitely large and infinitely old. And that model worked pretty well for about 200 years. Most astronomers accepted it. Until in the 19th century, problems began to emerge as new forms of evidence appeared and new technologies. Now, I'm going to describe this new evidence and how it undermined Ptolemy's universe very briefly. Your job is to dig much deeper into the evidence. So, let's go. What 19th century astronomers were really interested in was trying to map the universe. This meant two things. First, can you find the distance to stars? Can you tell how far away they are? And secondly, can you figure out how they're moving? Now let's begin with the problem of distance. Can you imagine, how could you figure out how far away the stars are? It's not easy at all. But in fact, the Greeks, who are really good at thinking about the universe logically and rationally, had already figured out how you do it. And the method is that of parallax. Let me try and explain. Now, take your finger, put it right in front of your nose, and now hold the finger steady and waggle your head. And notice that the finger moves against the background, okay? Now move the finger away, do the same thing, and what you'll notice is the finger seems to move far less against the background. Now, the Greeks had figured out that something like this might be true of the universe. If there's a star that's near us, it's a bit like your finger. You may see it moving against the background. And by figuring out how much it moves, you ought to be able to calculate how far away it is using trigonometry, which is the maths all surveyors use. But there was a problem. The Greeks simply didn't have the technology to make precise enough measurements, and the movements of stars, even the very nearest, are absolutely tiny. So it was not until the 19th century, when new, better telescopes emerged, that we were able to make the first parallax measurements and the first measurements of the distance to nearby stars. Astronomers also developed a whole series of other ways of measuring the distance to stars. I'll give you just one more example. It involves a special type of star called a Cepheid. Cepheids vary. The pole star is a Cepheid. An American astronomer called Henrietta Leavitt began to study Cepheids, and what she found out is that from the way they vary, you can tell exactly how bright they really are. Now, if you know how bright they really are, you can figure out how far away they are, because you can figure out how much light has been lost in between. So that's one of a whole series of ways of measuring the distance to stars. Now, astronomers also began to figure out ways of measuring whether stars are moving away from us or towards us. At first sight, that may sound impossible. The techniques are very clever. They're based on the principle of the Doppler effect. Now, you know, if an ambulance goes past you, the pitch seems to drop. It goes as it moves past you. We've all seen this, okay? What's happening is that the frequency is dropping as it starts moving away from you. Now, astronomers figured out that the same thing happens with the light from distant stars or galaxies. Its frequency drops. That means it's shifted towards the red end of the spectrum. So astronomers say it's redshifted. Now, if you find a distant galaxy is redshifted, that means it's moving away from us. In the 1920s, an American astronomer, Edwin Hubble, used the Mount Wilson telescope in LA to make an astonishing discovery. What he did was he used all the information we've just been describing, and what he found was, first, that most galaxies seemed to be moving away from the Earth. That was a surprise. But they found something even more astonishing. The further away they were, the faster they seemed to be moving away from Earth. Okay, think about this for a moment. What could that possibly mean? Well, it seemed to mean first that Newton's model of the universe simply doesn't work. The universe is not fixed in time and space. Instead, it's expanding. Now, for most astronomers, that was a quite remarkable and unexpected conclusion. Because if it's expanding now, think about the past. It must have been smaller in the past, and at some time in the past, it must have been infinitely small. That's what the Belgian astronomer Lemaitre called the primordial atom from which everything came. Now, this was a revolution. It was a revolution in astronomical thinking. And what it meant was that the universe, like you and me, has a history of change over time. But it took 40 or 50 years to figure out all the implications of what Hubble had found and to actually tease out that history.